We are live. All right. So today's topic is going to be the gradient method. So I just a very quick recap of what we talked about last time. We talked about the methods for one-dimensional minimization. Mostly there was this one-dimensional Newton method that was mentioned in finding the zero of the gradient, the zero of the derivative of g when we cast the problem into one-dimensional case in the line search problem. So just very quick recap into this template. So we are talking about this template of unconstrained optimization, which involves choosing an initial point, choosing a direction, search direction or descent direction, then choosing the step length, and then also part of the criteria is stopping criterion. So when do we stop? So last time we talked about the step length. So that would be step 3. And today we are going to be talking about these different directions, descent directions, finding directions into which we search. And the first and most prominent is what we call the gradient method. In the gradient method, what we do is the search direction will be simply the negative of the gradient. So we take the gradient because the gradient is, if you think about this, here the idea of the directional derivative comes into play easily. So if you think about the Gateau definition of derivative, so if you choose a direction and then the derivative with respect to that direction is, we proved in the exercises that the directional derivative into a direction is basically the dot product of that directional vector and the gradient. So the first approximation, or the easiest approximation of minimizing the function, is choosing the direction based on the derivative in the way that we pick the negative of the gradient, because then the dot product is maximized in absolute value, but it's the negative sign because it's in the negative direction of the gradient. So obviously, if you're perpendicular, at the right angle with respect to if you're orthogonal with respect to the gradient, then the dot product will be 0. If you're in any way in the same direction as the gradient, then the dot product will be positive, maximizing when you are at the same direction. And then if you go in the opposite direction, it's maximized when you go into the negative direction of the gradient. So we choose here the descent direction or the search direction as the place where f decreases fastest locally. This is also an example of what we might call a greedy method. So we are greedily locally looking at the best direction. And there is a theorem that can be proven, which we don't go to the proof here. But if we take the gradient method, then it will converge to a critical point of f, regardless of the point where we start from. But obviously, critical point means that it's 0 of the gradient. The problem with this is it may be a saddle point, in which case it's not necessarily it's not necessarily a minimum. Also, there is no guarantee as to whether it's not a local minimum. Well, that in general we cannot rule out in any case, and the step length can be selected heuristically or optimally. It doesn't really matter as long as we choose the step length in such a way that it's not enormously too big or very much too short. Choosing one that is too short is less of a problem. It just leads to a slower convergence. But the greatest weakness of gradient method in general is slow convergence, and we'll see why this is, and this comes from theorem 4.2. So the weakness of the gradient method is that if we use the optimal step length, meaning that we go all the way into the direction of the negative of the gradient to a point where that g, if we solve the line search problem, the g of t is its derivative as it's 0, then in fact we arrive at a point where the new gradient is orthogonal to the old gradient, so that the successive search directions will always be orthogonal. And in the exercise, we shall see that that there are situations which are not enormously difficult to optimize in general, but for which the this orthogonality phenomenon leads to very, very poor behavior. So the number of iterations that we're going to be having in a certain kind of function, the so-called banana valley function, or it's called Rosenbrock function as well. So it is a situation where we have like it's two-dimensional situation where we have like a valley, but the bottom of the valley is shaped like a banana. And in certain situations, this so-called Rosenbrock function, there are other versions of the Rosenbrock function as well. It's the simplest one. It results in a situation where it travels the valley almost at the bottom of the valley, but it bounces, you know, at right angles or almost right angles. And when it's getting closer and closer to the optimum, it starts taking very short steps because the valley is very what is the opposite of steep? I don't remember what the word is, but you know, it's very flat. It's very flat at the bottom, so it tends to bounce around a lot before convergence, and that we'll see an example of that. So the theorem is actually self-evident if you think about it. Now look at this proof. Let's say that we are looking for the step length. We are minimizing the function g t, which is basically your original function f, at your current point xk plus then t times dk, where dk is now the gradient. And if we take the derivative of this with respect to t, so we get xk plus tk dk, and then times dk, which is dk is the gradient. So what happens is we go to a place where this g prime is 0. Well, this means that the gradient at the f prime, you know, the derivative of f at that point is in fact the gradient. And that's actually when we go xk plus tk dk into that direction, then that point is where we get, that's xk plus 1. And the gradient at that point will be have a dot product with dk, the previous search direction, of 0, meaning that it's orthogonal. So if we choose the step length in such a way that we are doing an optimal in the sense that, you know, we go all the way until we get 0, then the next direction will be orthogonal to the previous one. Here's an example. If we have a quadratic function, so in general, second order polynomials or second degree polynomials in Rn can always be presented or represented by a function that is f of x is 1/2 times, well, it doesn't need to be 1/2, but you know, something times x transpose qx minus c transpose x. If in fact it's positive definite, then we know that it's convex. We'll show that shortly, but it's convex because, you know, actually we did show that. If we take its Hessian, then the Hessian of this f, or the second derivative of this f, will simply be the matrix Q, and Q being positive definite, it means that the function is convex. So if we have a convex second order polynomial and variables, it will have an exact minimum. And the exact minimum can be found at some point, x star. And if we look at the distance from it, we know that we will get a convergence with the gradient method, such that it's a linear convergence, and the m in that will be proportionate to what is called the condition number of Q. So the condition number of Q, you know, there's a linear algebraic definition here. We're going to have a short teamwork here. You look it up and see what the condition number means. But the basic fact is that if the condition number is large, then what happens is that the m, the coefficient in this linear convergence, is very close to 1, and it means that the function, the method will converge very slowly, even with quadratic functions. And with quadratic functions, the solution of the optimum is very fast. So that even in the simple cases, the gradient method, when you have the optimal step length and so forth, is not actually a very good idea, not necessarily. So while the gradient method has a very strong relative strength in it, that it is very simple to implement, just calculate the gradient, go in the other direction, and do this as many times as you can to find the minimum, then gradient descent methods in general, while they are guaranteed to converge to a critical point, it has two weaknesses. One, the speed of convergence may be abysmal, and two, it may get stuck at a saddle point, because if the gradient if you happen to stumble upon the saddle point and you go there from a certain direction, then you may actually reach the saddle point, and at that time the gradient is 0 and you won't be able to move anywhere from that. So now we'll have a short break from the recording, and I'm going to ask you to do a little bit of group work here. Sorry. So I'll just very quick recap. The condition number says you can take the geometric intuition from the condition number here, is that if your function, this is a quadratic example, but in general, if your function is such that in one direction, the valley, the bottom, you are looking for the minimum. In some directions, it's very steep, and in some directions, it's very flat. Then the convergence of the gradient method tends to be poor. Okay, and now we move to Newton method. So in the Newton method, we can basically just what we do is we approximate the function locally, not just by using the linear first order Taylor approximation, using the linear approximation of the gradient. We use the bilinear, also we append it with the bilinear optimization, bilinear approximation of the second derivative. So you can think of this as a generalized Taylor polynomial. You could have higher degrees here, but they would be far more complicated functional objects than just simple linear and bilinear mappings. So we'll be content in the Newton method to this is as hard as we go. So in the Newton method, you think of f at x. You are at a point xk, and you're moving from x to x plus d, right? Then roughly x is xk plus d, or d is x minus xk. So d is the direction. You're moving from xk to x. So the direction is x minus xk, right? So xk is fixed, and you're looking at different x's here. So f at those different points is roughly equal to f at xk plus the derivative of f prime at xk operating on d. And I say operating on d instead of times d. It's in our cases, f prime will be the gradient basically, and d will be the direction. So f prime, the gradient dot product d. Plus then 1/2 of the bilinear mapping, that is the second derivative. In this case, that will be the Hessian matrix multiplied from both sides by that directional vector d. So this will be our mkx. This is the approximation of f upon iteration k, if you move from xk to x, where d is now the direction. So we're going to be looking for a situation where this second order approximation has a critical point. And this is easier because now it's a quadratic form. Remember that fxk is a constant, f prime xk is a constant vector, f prime prime xk is a constant matrix. So this is basically a quadratic function. We're doing a quadratic or a second order approximation of the function. So this approximates it using a second order polynomial, if you will, at point xk. And it tells you our guesstimate of the value of the function at point x. And we look for an x in such a way that the gradient of this mk is 0. So we look for a point where there's a critical point of mk, right? So instead of finding the critical point of f directly, we look at its second order approximation and look for its critical point. So setting the gradient of mk, we can actually look at the gradient of it. So the gradient of it is simply the gradient at fxk plus then the f prime prime, which is the Hessian times x minus xk. This is the approximation of the gradient. And we set this approximation of the gradient to 0, then we can solve x. So it's simply xk, the current point, minus the inverse of the Hessian times the gradient of fk, f at xk. So in this iteration, we can find the next point, which is the critical point of mk, by simply taking the point xk and going into the direction where we take the negative of the inverse of the Hessian times the gradient. So this does, what does this do? It takes into account the fact that if you compare, let's compare this to the, let's just directly compare this to what happens in the gradient method. In the gradient method, we first take the negative of the gradient. This is a promising direction, and we go into that direction until the new gradient is perpendicular to this, or just not, it's orthogonal to this. And so we can solve, assuming that we solve the optimal step length. We don't have to go that far, but let's say that we solve the optimal step length. So we go to the negative of the gradient until such a point as the new gradient is orthogonal. So what do we do here instead is, I mean, let's just go back to the gradient method and tell us what this is. We use the first order approximation. We assume that the function is a linear, just straight line, and we go there and until it stops diminishing. In this case, we don't take this as just a straight line function. Instead, we take it, you can think of it as a multi-dimensional function, and we look at this now as a quadratic form. We approximate it locally as, we think that locally somehow we're at this point, the function, we get the Hessian and the gradient. So let's say the gradient points in that direction, and then we have the matrix. It doesn't point anywhere, but it's a linear operator, here. And from those, we formulate the second order approximation. So locally, we think of it as looking like a cup like this. I mean, there's just the Hessian tells us something about how it curves at this point, and the gradient tells us how steep it is at this point. And we use these two information to approximate it in a second order form. And then we look at the bottom of that second order form, and we go there. This is what happens in the Newton method. So we're kind of taking a little bit more accurate approximation than linear. We take, in the linear, we thought of this as just, it's straight surface until we hit the bottom. That's just the new direction is like this. So we hit a bottom. In this case, we think of it as a second order polynomial, and we hit the bottom of that. Okay. And here, the step length will be 1. There are issues here. Whereas the gradient method does converge globally, So we get to a point where the gradient method will bring us into a critical point, which is the zero of the gradient. The Newton method has some issues in it. It's not globally convergent. There are situations where the Hessian behaves in a way that it leads us astray, so which we will address shortly. This is a when it does result in a faster convergence than the gradient method in general, but there are situations when it doesn't. So the situation where it is in fact behaves very well is when a function is twice continuously differentiable in that way that the Hessian doesn't have any points at which it's non-continuous or undefined, and it's positive definite at the point of the minimum. Those are two conditions that need to be satisfied. Well, they don't need to be satisfied, but in order to guarantee convergence, those two have to happen, and also the so-called Lipschitz continuity. And the Lipschitz continuity says that somewhere around or near, when we are near the optimum point, there is a limit to how much the how rapidly the Hessian changes with respect to changes from moving from one point to another. Think of it as the Lipschitz continuity says that there is some kind of a limit as to what can happen to the Hessian. It's hard to explain how this goes in multidimensional cases, but it's not actually terribly hard to think of this in terms of one-dimensional case. I can give you a one-dimensional case in which it works pretty well. So think of the function. X to the power of 1.5, or x to the 3 divided by 2. And think about its derivative. Its derivative will be the square root of x. And it's the second derivative will be, 1 over the square root of x. Okay? And now the function itself is continuous. Well, let's assume that the function is defined in such a way that it changes its direction at the origin, so that we make it so that it's piecewise defined, so that when x is positive, the function is x to the power of 3 over 2, and when x is a negative, it's minus x to the power of 3 over 2 and in the negative. So we have like this, it looks like a little bit faster than linear, and then it just crosses the origin. I can draw a picture of what it might look like. It's a function like this. Let's say it's a function like this. And then we take its derivative, and even the derivative behaves relatively okay. Let's say its derivative looks something like this around the origin. But then when we take the second derivative of it, then the second derivative looks like this, so that when we are very close to the origin, then the proportionate change, when we move around the origin a little bit, then the proportionate change with respect to the second derivative will be very, very large. So it's not, strictly speaking, non-continuous, you know, both left and right hand limits approach zero there. But the change in around that point is so big that when you are very close to zero, it's almost infinite, the change in the second derivative around that point. I hope you understand what I'm getting at here. So this is a situation, and among one of the situations that is a problem with when we are using the Newton method. If the second order derivative, meaning the Hessian in this case, if it has a phenomenon similar to this was unidimensional, but in multidimensional, there are situations where the second derivative will incur very large changes, very large changes when we move from one point to another, proportionate changes by it, you know. So when we move just a little bit, there is a big dramatic jump, and when we are actually tightening the spot in my example here, if we zoom in on this, then the tiniest change in x will result in arbitrarily large proportionate change in the second derivative. So if this kind of situation happens, it's not Lipschitz continuous. Otherwise, it's Lipschitz continuous. If it is Lipschitz continuous, it means that there is no abrupt, in this case, approaching proportionate change approaches infinity. This does not, when this does not happen for f, then we are, you know, for the second derivative of f, then we are in the clear. You know, as long as that doesn't happen near the optimum, and if we are not too far away from the optimum, then we will be able to find the optimum. When I say optimum, I mean local minimum. Obviously, this can find you a local minimum elsewhere, but if we are very close to the true minimum, then it converges. So obviously, for difficult problems, this initial guess has to be very close to the true minimum. Otherwise, the method may give us really bad behavior. So this week's exercise, the last exercise, we have a situation where this happens. We will reach a saddle point if we start at a bad situation with the Newton method. So we'll look into that example even more closely. So be mindful of this phenomenon. Okay, so what can we do? What can we do with this Newton method now that you know, we know there is this risk? Well, one way to do this is to check whether the Hessian is positive definite. If it's not, then do something else. The positive definiteness of it is in the conditions of convergence. Lipschitz continuity, well, that's a bit tall order. It's not always easy to figure out when it is Lipschitz continuous near the optimum. We can't really in general say that. So for that, there's a problem. But let's look at the positive definiteness argument. The thing is, if the Hessian is not positive definite, then depending on which way the gradient points, when you multiply the gradient with the inverse of the Hessian, it may actually, you know, that it's not positive definite means that it has it has negative or zero. Well, if it's, yeah, it has negative eigenvalues. So there are directions in which if you take a vector, then multiplying it with the Hessian results in that vector flipping direction. And the thing is, if you take the inverse of the Hessian, the same thing applies. If you take the inverse of the Hessian and the Hessian is not positive definite, also the inverse will have negative eigenvalues. So that if you multiply the gradient with the inverse, there is a chance that that will actually lead into increased direction, not a decreased direction. So you end up worse off. The algorithm may diverge, or it may converge to a point that is a maximum or a saddle point. This is also possible. We actually saw this in the exercise, this week's exercise, in the this week's final, the 6th exercise. There is a situation where if you use the Newton method to calculate the minimum, then you will find that the point that you reach will be a saddle point if you start at the wrong point. We can then modify the search direction a little bit. One way is to, and this is something like you can check this out. In fact, I'm going to have a small break now, and I'm going to ask you guys to look into this and look into these different methods that are not mentioned here. I'm going to pause the recording and give you. We'll resume here just so that we get to this. So in the modified Newton method, you can think of as using the matrix G, which is obtained by taking the matrix, the Hessian matrix, and then modifying it by adding into the diagonal some constant mu k. Adding this constant on the diagonal will in fact result in all of the eigenvalues of this matrix G being scaled, or the matrix G as having the eigenvalues of this Hessian, but increased by mu k. So we'll talk about this, choosing these mu k in a way. So this gives us a new search directions, and this is considered to be one of the best methods for solving a free minimization problem, provided that this second order derivative is easy to compute. This is fast and dirty. Choosing, and it does. The beauty of this is that the mu k choice of mu k is not actually all that critical, as long as it makes the gk positive definite. In this case, the new search direction can be found fairly easily, and you can think of this as this can be to an extent. I'm not saying that it as such, but to an extent, this can be thought of as fixing the direction by going towards the gradient. The alternative way is just to use the Newton method's search direction and then tilt it towards the negative of the gradient. That's an alternative way to do this. They're not equivalent as such, but they have a very similar effect on the search. So you can modify it in one of these two ways. There is also a possible way of tinkering it with even a little bit more, so that you compute a diagonal matrix where instead of having just all around shifting of the eigenvalues, you have a diagonal matrix where you fix each of these directions separately, or each of these diagonal elements separately, to make it positive definite. This has the upshot that you can more readily fine tune this method, but this is somewhat involved in calculation of this Cholesky factorization, and not going to go there. We can do this if we want, but we're not really see a point in going into it that much.
Before we move on, I had maybe a straightforward question. I know from linear algebra that if a matrix is positive definite, then it's invertible.
Yeah.
So if it's not positive invertible, it shouldn't be invertible.
Well, if it's not possible, it can be invertible. I mean,
okay.
It can be invertible. The thing is, I like to think, I mean, this is not necessarily a generally recommended way of thinking, but I like to think of the matrix or the linear operator that the matrix represents as being represented through its eigenvalues and eigenvectors. And if we think about what is going on here, the eigenvalues, if they are non-zero, all of them are non-zero, then the matrix is invertible.
Yes.
If they're all positive, then it's positive definite. And if some are negative, then it's not positive definite.
Okay.
And if there are no zeros there, it's invertible, whether they are negative or positive.
Okay. Okay.
Yeah. So, but if you think of it through these eigenvalues, then yes, this is actually the mu k can be selected as long as mu k is positive and larger than in absolute value than the most
zero eigenvalues.
Yeah, most negative eigenvalue, then this G matrix will be positive definite.
Okay.
Because this will shift the eigenvalues. We can look at it through. I'll just very quickly show you. We can look at it through the eigenvalue equation. Because if you think about what the eigenvalues are, you can get the eigenvalues of H by finding the determinant of H minus lambda I is 0, right? You said these are the eigenvalues are the values that lambda. So we have I is the identity matrix, H is now our, let's say it's our Hessian. And this equation, setting the determinant of this H minus lambda I to 0 gives us the eigenvalues of the matrix H. And now instead, if we write G is equal to H plus mu I, right? If we put it as G as H plus mu I, then its eigenvalues can be gotten by determinant of G minus lambda, I'm going to change I is 0, right? So if we rehash this as determinant of H plus mu I minus lambda G I is 0, right? Then we get that this is equivalent to the determinant of H plus mu minus lambda G I is 0, right? Now, this means that this mu minus lambda G is in fact the eigenvalue of this G. And for it to be, all of them to be positive, we have mu minus lambda G is greater than 0. And if and only if mu is greater than sorry, it should be minus there, minus. And sorry, it should be like this. So it's, I wrote it wrong. So I made a small bit. So it's H minus mu plus lambda G I is 0. So if I rewrite this again, I get this mu minus mu plus lambda G. That should be greater than 0. And it means that mu must be smaller than minus lambda G. So we get here that as long as mu is smaller than minus lambda G, sorry, it should be greater than, sorry, as long as mu is greater than minus lambda G, where lambda G is the most negative eigenvalue of H, then the determinant of, well, then the eigenvalue of G is positive.
All right.
Yeah,
I got it. That was clear.
Yeah. So yeah, that's why it works. That's why it works. All right. The algebra there was not perfect. I'm sorry, but the intuition should be relatively straightforward. Right. So that modified Newton method is, it's very simple to implement. You know, just calculate the Hessian and so on. The problem comes when we have a high numerosity or high number of very high number of variables, because or if the second order derivative is very hard to come by and calculate. So it turns out, I mean, think about it. Let's say you have 10,000 variables. Okay, then if you calculate the gradient, you take 10,000 steps in calculating each component of the gradient, and then you go in that direction, and 10,000 steps for each iteration for that. But if you have if you calculate the Hessian, that Hessian itself has 100 million components to it. Even if it's a sparse matrix, saying that many of these components of F have no interplay with each other, then the gradient, I mean, then even so you have a situation in your hands where you are actually, when you're calculating the Hessian, you're calculating millions or tens of millions or even hundreds of millions. When you have thousands of variables, you will be usually doing millions of computations in computing the Hessian, not thousands. So the order of magnitude increases very much when you increase the number of variables. Okay. And it turns out that if you have a large number of variables, then most of the work, computational work in calculating the Newton method, is done in updating the Hessian. So you calculate the new Hessian's value of the for each of these component of the Hessian, and that takes a lot of time, a lot of computational effort. So the basic idea here is that, okay, let's not recalculate the Hessian. Let's not spend too much time on calculating the Hessian, because it takes a lot of time. Let's do something that gives us an approximation of it. So this so-called quasi-Newton method can be used to approximate the Hessian, or the effect even of the inverse of the Hessian. Really, what we want is to figure out a matrix that might be similar to the matrix that is used in the modified Newton method, but without having to compute the Hessian. So we maintain a approximative matrix called HK. And it doesn't actually even have to be a matrix per se, as long as it's something that gives us a flavor of multiplying with the matrix, right? So, and what we do by multiplying with this matrix is simply, it's simply the idea is that we figure out where to go by using this matrix, and this H0 is an approximation of the Hessian initially, and then in each iteration we calculate new HK, which can be obtained by updating the HK minus 1, or HK plus 1 is obtained by updating HK without having to resort to calculate the whole matrix all over again. So we try to avoid calculating the second derivatives. but we want to have something that approximates it or gives us some kind of approximation. And in general, I mean, if you think about it, tens of millions of computations is not a problem if you do it every once in a while. I don't really care what happens every now and then. It's if you do it on every iteration. And in this case, because you don't actually have the exact direction, you also need to solve the step length. I mean, the same holds actually in the modified Newton method. When we use the modified Newton method, we should really be careful in calculating the step length, because if we're modifying the matrix a lot, we can't just go into this new direction blindly, you know, hoping that the matrix is doing the job. So instead, we also need to figure out in the modified Newton method, we need to figure out the step length. So if you use a pure Newton method, it gives us the step length. That if the Hessian is well behaved and all that stuff, then equation 4.4 directly gives us the iterant, the new iteration. But if already when we go to modified Newton method, we've already messing up with the matrix, so we can't really be sure if our mu k is enough to you know, if it's small enough to warrant directly going to this decay. Instead, we go in this direction decay, but we still have to figure out, it comes at a cost, at having to reintroducing the step optimization. And this is doubly true for the quasi-Newton method. So the quasi-Newton method follows the same template. It's only that we are at all iterations in calculating the search direction, we are really using this current approximation of or guess of what stands for the Hessian. It's not the Hessian, really, it's not the second order derivatives, but the idea is that we want something that behaves in a similar manner and gives the similar benefit to our search. So when we are at an iteration, we start by solving our dk from the equation hk dk is the negative of the gradient. So our hk stands for the Hessian thing, and we should have this property that the direction, search direction times the Hessian should be the negative of the gradient. I mean, it's the same as in the Newton method, but in here, this hk, you can think of it as a matrix, but you can also think of it as something that changes the direction of the twists, or takes into account the second derivative and twists the gradient a little bit so as to modify it and take into account the second order effects. But it doesn't, you can think of it as our approximation of the Hessian if you want to, but you can also think of it just in general as some second order information about the change in the change of things, like the change, how is the gradient going to change? So we're kind of preempting the change in the gradient. So just to give an intuition about what we try to do, remember that in the gradient method, if we have two successive search directions, they will be orthogonal and they'll be like this. So the first negative of the gradient in this direction, and the second negative is in that direction. We will actually, two consecutive steps will look like this. We first go here and then we go there. But the Newton method can be thought of as, okay, what if we go directly there? We do better, right? That's an idea. And the modified Newton is that, okay, it's going to, you know, in the modified Newton method, you know, we are like, okay, it may be this matrix may not be a good idea in finding what that direction is, but we're kind of twisting it a little bit, I mean, like this. And this quasi-Newton method is just something like, okay, there's this change and the previous change was like that, so we're going to fix this a little bit, so maybe we'll go about that much that way. You can think of it this way as well. So we at all points when we find a new iteration xk, then we're going to update the matrix hk by some delta k. And this delta k here, this capital delta in step 5, before we stop, is what we need to discuss, what we want to do next. We can go with what we were discussing already in the univariate case, the second or the secant method. And now we're just generalizing it into these multi-dimensional things, these vector things. So remember, in one-dimensional case, the second order derivative is roughly equal to, if the change between x and xk minus 1 is small enough, then the second derivative can be thought of as if these changes, if we are moving in very, very tiny steps, then the second derivative at xk can be approximated by looking at the change of the gradient when we moved before, and then looking at the change of x when we are moving now, and dividing that. So it's proportionate. So when xk minus xk plus 1 approaches 0, then f prime xk minus f prime xk minus 1. And think about this, so that the spaces between these different iterations is very small. So these changes both go towards 0. So this actually approaches the second derivative of the function at this middle point. So this is an approximation, and the smaller the steps between xk and xk minus 1 and xk and xk plus 1, the smaller those changes are, then the better this approximation is. But we can't divide by vector because xk minus xk plus 1 is a change in the vector. But if we multiply it with the vector xk plus 1 from the right-hand side, so we get something that is that does make sense. Remember, the second order derivative is a matrix. So if we're multiplying with this matrix f prime prime xk, and we're multiplying xk minus xk plus 1, so the change in there, it's roughly going to be equal to how much the gradient changed. So that actually it does seem to step from xk plus 1 to xk minus 1. I'm thinking, well, look at 4.5. There's a little bit of a confusion there. That's using xk minus 1 there. It should be actually xk minus 1, not xk plus 1. You're right. Not you're right. No one mentioned that, but I now understand that there was a, because if it weren't like this, then that doesn't actually make a lot of sense. Yeah, I was trying to make sense of it, but there's actually a typo. It should be xk minus xk minus 1. Sorry about that. I was trying to make sense of something that doesn't actually make sense. So I was explaining it very well, even though it didn't make a lot of sense. So sorry about that. So in the equations before 4.5, it should be xk minus 1, not xk plus 1. But it doesn't matter. I mean, I hope you get what I mean. The relative change of the derivative with respect to the relative change of the point. And we're doing this with vectors. So we are looking for a matrix hk plus 1 such that the change from xk plus 1 minus xk should be equal to the change in the gradient of f when we move from those points. So the matrix should have this property that it approximates the change in the gradient when we multiply it with the change in the point. And this is called the quasi-Newton equation. So from this equation, any matrix that actually satisfies or gives us a good approximation that closely gives us this idea of 4.5 is a good matrix for that. in the quadratic case, the Hessian satisfies this exactly. In general, it doesn't, because even the second order approximation is not a perfect approximation. But this is good. It's a good idea. So the equality in 4.5 should not be viewed as strictly being equal. It's what we strive for, but as long as we're approximately doing 4.5, then we're doing very well. And here are some of the updates that are mentioned for that. I'm not going to go into them currently, and I'm not going to actually do them in detail. We have some requirements in it that if we are using the inverse, or we are trying to approximate the inverse of the Hessian, or trying to maintain a matrix that instead of maintaining the approximation of the matrix itself, we maintain the inverse of the Hessian, then we can use this different approaches here. We have some requirements such that we should maintain symmetricity and positive definiteness. The reason for this is that the Hessian is always symmetric, and the Hessian, while not always positive definite, then we want whatever the matrix there is to be positive definite, even when the Hessian is not. And these updates, matrix updates, or this BFGS updates, we'll look into this in the exercises. These formulas, we can do them. The difference with the Broyden and the BFGS is that the Broyden updates the inverse directly, whereas the BFGS updates the approximation of the Hessian. So we can't directly use this formula. There is an exercise where we do it. You can't directly use this formula. Instead, we use its inverse, or you know, here when we do the BFGS and we use the HK here, then we use its inverse, or we use the B matrix in the Broyden, then we use that not as an inverse, but as the matrix that actually multiplies the gradient. So we'll take a look at these in the exercises next week. I'm going to skip this latter part of it, and this lemmata here that derive this. You can look at these DFP updates and these BFGS updates. I'm going to skip them because this is very algebra heavy, serves very little purpose in developing our intuition into how this thing works. It's a good topic if you are interested in this kind of linear algebra power building or bodybuilding. Then just go ahead and study this and explain this in your modeling exercise if you want to. That's one possible way to do a project on. I wouldn't recommend it. It's very hard work, but if you do like and enjoy linear algebra, then by all means go with it. But I'm not going to require them. We can try these results then in the exercises. And there's some convergence results as well. Convex functions will have a very good convergence in these updates. Sufficiently regular functions, whatever that means, will have a superlinear or Q-superlinear convergence given the correct suitable strategies. Also, this theorem that states that if you have a critical point at which the gradient is 0 and the positive definite Hessian at that point with Lipschitz continuity, then these algorithms converge, provided that we are doing a suitable step length strategy. So these are not something I ask in the exam, but you can revise and review them if you are going to be using some of these methods later on. The thing is, for the choice of this initial approximation, if it's handy to calculate the Hessian in some cases, then you can calculate the Hessian and start with that. Other possibility is to simply start with the identity matrix, which is surprisingly effective. You start with the identity matrix. So the first step of the algorithm will be simply gradient descent. And then the successive steps will take into account the previous gradient changes. So that's perfectly fine as well. Okay, we'll stop here. We're going to talk about the conjugate gradient method next week. Hopefully we will be able to move to constraint optimization already next week, but maybe not. I'm going to stop recording now. If there are any questions,